Welcome back to the deep dive. Today we are doing a really focused examination of, well, the engine room of modern drug discovery.
That's a good way to put it.
Our sources are showing that we're officially past the era of just predicting what a molecule is. We are now, it seems, in the era of actively commanding the design of new, life-saving biological entities using AI.
That is the core mission. We're charting a path toward what you could call truly autonomous biological engineering. And that really requires three major components working together.
Okay.
And so we're going to unpack these three pillars for you. First, you have the design engine itself, something called BoltzGen, which is a generative model that acts as a kind of universal molecular designer.
Right.
Second, you need a reality check. We have that from the FoldBench study, which gives us a really unvarnished look at where these models still stumble.
Finally.
And finally, the essential safety net. The validation tools, CONFIDE and CODE, which are designed to solve the very dangerous problem of what's being called structural hallucination.
Exactly. I mean, the promise of designing a new nanobody or a protein to hit a specific target is incredible, but that power is kind of meaningless if you can't trust the output.
You can't.
So we're setting the stage. New generative power, clear metrics for failure, and built-in theoretical checks for success. Let's unpack this, maybe starting with the design capability that promises to change everything. So when we talk about universal design, that feels like a major leap in, versatility. Let's start with BoltzGen. What makes this model so foundational right now? What does universal actually mean here?
BoltzGen is fascinating because it's an all-atom generative model. It performs both structure prediction and design in a single unified system.
Okay, so it's not two separate models.
No, it's one.
Fair.
The universality comes from its modality-agnostic approach. It doesn't just design proteins. It can handle proteins, nucleotides, small molecules, and targets, and then design a binder for them, often mixing and matching.
And crucially, it allows the scientist, the user, to really direct the creation process, not just suggest, random mutations.
Exactly. That's achieved through what they call a design specification language.
Language.
Yeah, and this language lets you impose these really complex, non-negotiable constraints on the generated structure. So you might specify a certain binding pocket you needed to interact with, or you can build in specific chemical realities like ensuring you include covalent bonds like disulfide bridges.
Wait, you're saying BoltzGen can specify covalent bonds? That seems incredibly difficult to validate. Does the model somehow predict the reactivity too?
Not the reactivity, no. It predicts the structure that allows those bonds to form, which of course increases the likelihood of stability. So when you specify disulfide bonded peptide, you're usually aiming for a highly rigid structure, maybe a cyclic peptide or a helicon.
Yeah.
This is huge for drug diversity because it means the AI can start designing these incredibly stable molecules right from the start.
Okay, let's get to the headline numbers, because this is where the design engine really proves its real-world value. BoltzGen was put through a brutal test, right? Designing binders against 9 novel protein targets.
And these were targets so new that none had a known binding partner with more than 30% sequence identity in the entire protein data bank, the PDB.
And for our listeners, the PDB is basically the massive online library of all known 3D biological structures. So if there's nothing similar in the library...
The AI can't cheat. It can't rely on memorization. It has to truly generate something new. And the success rates were, well, genuinely surprising, especially when you think about the economic constraints they put on this. They didn't test thousands of designs.
How many did they test?
For both the nanobody and the protein binder designs, they only tested 15 or fewer designs against each target.
15. And despite that really low sampling, you still had a high hit rate.
A very high hit rate. 66% of the targets yielded nanomolar affinity binders.
And for context, nanomolar affinity is...
That's the gold standard in drug discovery. It is. It means the molecule binds its target effectively at extremely low concentrations, which is exactly what you want for a safe and effective drug. Getting a 66% success rate on brand new targets where nobody knew what the answer looked like, is a phenomenal starting point.
Just to put that 66% into perspective, what would the equivalent success rate have been, say, 3 years ago, using more traditional methods?
Oh, wow. Using something like phage display or directed evolution against totally novel targets, you'd be thrilled with 5% to 10% successful hits.
Oh, massive jump.
A massive jump. And that would be after optimizing maybe hundreds or thousands of candidates. BoltzGen basically eliminates that initial costly screening process.
But if 66% success is the ceiling, what's happening to that other 34%? Is that a limitation in the filtering, or is it a flaw in the generative model itself?
It's often the filtering, and that really points to the difference between a structurally perfect molecule and a biologically viable one. The designs from BoltzGen go through this critical filtering stage where they get ranked using physics-based metrics to assess developability.
So they're looking for the structural equivalent of red flags.
Exactly. They look at hydrogen bonds, salt bridges, buried surface area, all metrics for stability and how strongly it interacts. But the biggest red flag is the size of the largest hydrophobic patch.
Okay, why is that so important?
Well, if a protein design has a big, exposed hydrophobic area, it's going to act like oil in water. It'll aggregate, clump together, and it won't express correctly in the cell. It'll fail immediately in the lab.
So by filtering those out?
By filtering for structures that don't have those oversized hydrophobic patches, they make sure the output isn't just structurally sound, but also biologically viable and actually expressible.
That makes perfect sense. A design is only step one. It actually has to be manufacturable. So BoltzGen shows us the ceiling of AI design, that remarkable 66% success rate. But the FoldBench study is a good reminder that a ceiling doesn't exist without a floor. So we have to ask, where do the current state-of-the-art models, even the most advanced ones, still fall down?
The general and kind of recurring weakness across almost all the current models is some degree of memorization. They perform beautifully when the targets look like something they saw in training.
Right.
But that performance declines steeply, even dramatically, in these data-scarce domains. They rely too much on familiar patterns when they need to be truly inventive.
And the poster child for data scarcity right now is nucleic acids, especially RNA. Why is that specific challenge so, well, largely unsolved?
It's purely a data problem. It's a ratio problem in the PDB, that molecular library we mentioned. As of May 2025, nucleic acid structures only account for about 8% of the 237,000 entries in the PDB.
8%. That is a tiny training set for a system that thrives on massive amounts of data.
Precisely. And that scarcity is compounded by the structural complexity of RNA. Unlike the relatively ordered folding of many proteins, RNA is heterogeneous, it's highly flexible, it uses non-canonical base pairs, and has these dynamic long-range interactions that are just very difficult to predict.
So this combination makes it a computational nightmare.
Exactly. Reconstructing the overall architecture is a nightmare.
And we saw a great example of this failure in the source material, showing how a model can be locally confident while being globally completely wrong.
Absolutely. The perfect example is the AlphaFold 3 prediction for the RNA aptamer 7ZJ4. The model was highly confident about the quality of local bits and pieces. It got a good local quality score, an LDDT of 0.68. But the global structural error was massive, an RMSD of 20 angstroms.
Okay, let's pause on those terms because they're critical. What does an LDDT of 0.68 and an RMSD of 20 angstroms actually mean to a scientist in the real world?
Think of it this way. LDDT is assessing the quality of your building materials, the individual bricks. That score of 0.68 means the model correctly predicted the shape of small local features. The bricks themselves are perfect.
Okay.
But the RMSD measures the overall difference between the predicted shape and the actual shape. An RMSD of 20A is an enormous error. It means the model assembled those perfect bricks into a structurally impossible building, one that would collapse. It's useless.
So if it gets the global structure wrong by that much, the molecules, it's fundamentally unusable.
Completely unusable. If the overall shape is wrong, the binding pockets are in the wrong place, the surface chemistry is wrong. It won't fold, it won't bind. It's a structural hallucination that looks plausible at the micro level but fails at the macro level.
And beyond RNA, what other key interfaces are still major challenges for these models?
Well, the world of therapeutics gives us two really complex scenarios. First is antibody-antigen prediction. Antibodies are built for diversity, and that diversity comes from the complementarity determining regions, the loops that do the binding.
The CDR loops.
Exactly. And prediction success often hinges entirely on modeling the CDRH3 loop accurately, which is the most variable and flexible region. Models just struggle when that loop changes shape tematically when it binds its target.
And the second major challenge is internal finding those less obvious binding pockets.
That would be allosteric sites. These are sites far away from the main binding pocket that, when something binds to them, change the protein's shape or activity. They're difficult because, going back to memorization, the training data is just heavily overrepresented with orthosteric complexes, the primary, most obvious binding sites.
So the model is biased toward the obvious answer.
Exactly. The AI is constantly getting distracted by the obvious location, which leads to ranking bias and, well, frequent misidentification when it's trying to find that subtle secondary allosteric site.
This leads us directly to the most critical problem here, structural hallucination. The machine is confidently wrong, high confidence score, but the structure is physically impossible. If we can design molecules with BoltzGen but can't trust the output, the whole process breaks down. So what's the new mechanism to trust these structures?
This is where code and confide come in. And to understand them, we have to look at the deep fundamental theory of how proteins actually fold. Traditional metrics like PLDDT, they capture what we call energetic frustration.
Okay, what's that?
That's the energy penalty associated with the final state of the structure. Basically, how stable is the final knot?
But you're saying there's another type of frustration we need to consider.
Yes. Structure prediction is also governed by topological frustration. This is related to the complexity of the folding pathway, the actual sequence of movements the chain has to make to get from a linear strand to a final 3D shape. It's about connectivity and backbone constraints. Code quantifies this often overlooked topological frustration.
Can you give us an analogy to make that a bit more accessible? Topological frustration.
Sure. Imagine you're trying to fold a rope into a very specific, complex knot. Energetic frustration, or PLDDT, is just checking the tightness and stability of the final knot.
Right.
But topological frustration, code, is assessing how hard it was to get there. Did you have to twist the rope violently? Did you get tangled up and have to start over multiple times?
So code is looking at the AI's rough draft of the molecule.
Precisely. Code stands for chain of diffusion embeddings. It tracks the generative trajectory of the model, the steps it takes to go from random noise to a final structure. If the model had to constantly scrap its work, backtrack, or violently twist the structure into place, that signals high topological frustration. It means the molecule is inherently difficult to fold and probably fake.
And this approach actually worked when they tested it against how fast a protein really folds.
It did. This is the smoking gun.
Code showed a surprisingly strong connection to physical dynamics. It achieved a Spearman correlation of -0.818 with experimentally measured protein folding rates, which are driven by those very topological constraints.
That's a huge finding. Folding speed is critical for how a protein functions.
It is. And you contrast that NEVIC 0.818 correlation with PLDDT's weak correlation of only 0.327. Code showed 148% relative improvement in capturing this dynamic, functional property. It's measuring the inherent difficulty of the shape, not just the AI's confidence in its final answer. So CONFIDE is the unified metric, then. It combines the energy metric, PLDDT, and this new topology metric, code. How effective is this unified approach at detecting those dangerous hallucinations, especially in really complex drug systems?
We have to look at molecular glue ternary complexes. They're notoriously challenging because you have three molecules interacting at once. These systems often produce structures that are physically impossible, showing what are called atomic clashes.
Where two atoms are closer than they can physically be.
Exactly, closer than 1.5 angstroms. It's like trying to force two billiard balls to occupy the same space.
And the old confidence score, PLDDT, just fails to flag this.
It often misses them completely, giving this false sense of security. But code achieved a 100% improvement over PLDDT in correlating with the number of atomic clashes, a correlation of 0.36 versus 0.18.
Why? What is it seeing?
Code can detect these physical impossibilities because trying to force two atoms together causes the generative model to experience extreme topological frustration in its process, and code picks up that distress signal.
That immediately accelerates the validation process. You're not moving forward with designs that are doomed to fail. And finally, connecting this to a really critical application, predicting drug resistance. Does CONFIDE help anticipate failure before it happens?
Yes, and this is arguably its most compelling real-world use case. They tested its ability to predict affinity changes from resistance mutations in the BTK protein against the inhibitor fenebrutinib. CONFIDE achieved a robust Spearman correlation of up to 0.83 with the experimental results.
Why is that so critical? Because PLDDT was basically useless in that same scenario, wasn't it?
Correct. PLDDT had a negligible correlation of just 0.03. See, when a drug resistance mutation happens, say it adds a bulky amino acid that physically bumps the drug out of the pocket, the model needs to detect that increased steric hindrance.
That physical clash.
Right. If the AI fails to model that clash, PLDDT gives a misleadingly high confidence score. But CONFIDE, by capturing the resulting high topological frustration from that impossible conflict, accurately flagged the loss of binding. It aligns perfectly with the lab results.
So it's not just validating structure, it's anticipating biological function and, importantly, failure points. So what does this entire stack of sources mean for you, the listener, as you think about the future of medicine? We've covered a lot, from generation with BoltzGen to validation with CONFIDE.
I think the key takeaway is that the drug discovery loop is rapidly closing, and the safety mechanisms are getting smarter. We now have these universal design models like BoltzGen, creating complex new binders with a remarkable 66% success rate against brand new targets.
Which dramatically accelerates the start of discovery.
Right, and at the same time, we have these sophisticated, theory-driven validation tools like CONFIDE that ensure those designs are sound, both topologically and energetically. It protects against these costly, dangerous failures from AI hallucinations.
But the benchmarks tell us the story isn't over, especially in the world of flexible molecules.
Not at all. The next frontier is clearly solving structural prediction for flexible molecules, especially RNA. That scarcity of data, that measly 8% representation in the PDB, is the single biggest computational bottleneck preventing the models from moving beyond memorization in that area.
We just need more data on flexibility, on conformational change.
We do.
Which raises an important question for you to think about. If generative AI can now design new, life-saving molecules with this kind of success and reliably detect its own subtle structural mistakes by analyzing its own thought process, what happens when that data scarcity, especially for complex nucleic acids like RNA, is finally resolved? What complex dynamic biological machines, not just single molecules, but entire cellular processes, will AI learn to build next?